Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Chemistry Unit 5 for May 2021. We'll begin with Section A. So Section A is of course 20 marks. I'll go on to the first question. The first question says, in which of the following pairs does the metal have different oxidation numbers? So let's see here. Okay, if we are looking at the oxidation numbers, we can see that this is chromate 6. Here the oxidation number is plus 6. Now, if you do not know how to calculate the oxidation number, let me give you an example. If we have something like that, since we are looking for the oxidation number of the metal chromium, I can call it X. And since we know oxygen is always minus 2 except in this situation, so let's see if it's in hydrogen peroxide, if it's oxygen attached to fluorine, or if it's oxygen in elemental state. They are going to be different oxidation states. So any other compounds that have oxygen in them, it will always be minus 2, except in these circumstances. Now we know that if this is minus 2, yet we have 4 of them, it's going to be 4 times, minus 2 times 4 becomes minus 8. And everything is equal to the overall charge on the ion, which is minus 2. So I'll put it the other side. So X is equal to minus 2 plus 8. And this gives us a plus 6. So that is how you can calculate the oxidation state. So for chromium, I can see it's plus 6. Let me try to show you how I would calculate the oxidation state for dichromate. So since we have chromium, again, so let's see Cr2O7 2 minus. If I call each of these X, so this is going to be 2X. Since each oxygen is minus 2 times 7 gives us minus 14. This is going to equal to minus 2. So 2X will equal to 12 and X will equal to plus 6. As you can see, that is also plus 6. So when you use the same formula, you can find that this is going to be plus 6 as well, and that is plus 6, that is plus 5, that is plus 5, and this will be plus 5 while that is going to be plus 4. So the answer should be D. I can go on to show you how I came across the answer, the final answer. So if we see VO2 plus, it means vanadium, let's call it X. Oxygen here is minus 2. Minus 2 times 2 becomes minus 4, and this is all equal to positive 1. So X will equal to 1 plus a 4, which gives us a 5. That is how we get the oxidation state of vanadium 5. Now to find that of this vanadium 4, it will be VO2 plus. We know if vanadium is X, each oxygen is minus 2 is equal to 2. So X will equal to 2 plus 2, which is a plus 4. And that's how you calculate the oxidation state of each. You can apply that to answers in B, as the part B, this part here, and as well as that part. So question 2 says, this question is about the reaction. So we have this reaction here. Let me use another color. And they say the electrode potential for the ion 3, ion 2 electrode system is that. So they say, what is the electrode potential for the titanium, titanium to titanium electrode system? One thing we need to know is you look at what is occurring here. Here we can see, let me use a different thing. Here we can see that ion 3 is being converted into ion 2, and therefore when we look at that electrode system, this is reduction occurring. So we can see a reduction reaction occurs. And we know if you have an electrode system, let's say 2 cells set up, this side and this side, whatever the electrons are generated on this side and they move to the other side, it means this cell here is going to gain electrons, and therefore reduction will occur there. So the one that gets reduced is always put on the right side. As you can see here, I wrote here, this system ion 3 to ion 2, it's going to be reduction, so you position that on the right, meaning since the other is going to be oxidized from titanium to titanium 2, it should be on the left because it's going to be the one releasing electrons. Then after knowing that, and since we have that E theta for the cell as well as this electrode potential, we can feed them into this equation. This equation says the E theta for the cell should equal to the E theta on the right hand half cell minus the E theta of the left hand half cell. So since we know the E theta for the cell is that, and we know that the E theta for the right, remember we said you put the ion 3, ion 2 on the right, so this is going to be 0.77 minus the E theta for the cell. When we make the E theta for the cell, the subject, this is going to become negative 1.63, which gives us B as the answer. Please remember to refer to what I've written here in order to help you understand it better. So I will go to the next question. Question B says, what metal should be used for the electrodes in the cell for this reaction. Now remember, we have an iron 3, iron 2 half cell. Here, since we have iron 3 and iron 2, we have two different ions made from the same metal. We cannot use iron as the electrode. The electrode has to be platinum because platinum will not interfere with the electrode system. And then on the other side, we have titanium 2 plus and titanium. Here we can use titanium metal as the electrode because of course we do not have different ions, we just have one ion and then the titanium solid. So the answer here should be a C. When we go on, they say the half cell for the iron 3, let me use this, iron 3, iron 2 electrode system is prepared by mixing equal volumes of solution of iron 2 sulfate and iron 3 sulfate. So here, if we are mixing equal volumes, what you need to know is in 1 mole of iron 3, as you can see, iron 3 sulfate, we see there are 2 ions. So it will produce twice, two iron 3 ions, while in here there is only 1, it will just produce 1. So if we are mixing equal volumes of each, it means this, because this one is producing 2, we have to ensure that this is also producing twice. And to do that, the equal volume, this one should have a higher concentration if we are mixing equal volumes. So the iron sulfate should have twice the concentration of the iron, the solution of iron 3 sulfate. So iron 2 sulfate solution should be twice, its concentration should be twice the concentration of the iron 3 sulfate in order for them to be mixed in equal volumes so that you can obtain the same concentration in the solution you have mixed. So I did some working down here before we select the answer. I say, again, iron 3 sulfate produces 2 moles of iron 3 plus, while iron 2 sulfate produces 1 mole of iron 2 plus. So if we mix equal volumes of each, the concentration of the iron, this should be half the concentration of the other. And therefore, the only answer that makes sense is you need to use 2 moles per decimeter cube, iron 2 sulfate, and then 1 mole per decimeter cube, iron 3 sulfate. The reason is, in here, we're going to produce 2 Fe3 plus, while in here, we're going to produce just Fe2 plus. Since the half cell should have equal concentration of each of the ions, it means when we had equal volumes, the volume is going to double. From, imagine you have, let's say, 1 decimeter cubed, and here we have 1 decimeter cubed. When we combine them, we're going to have 2 decimeter cubed, so the volume has doubled. It means the concentration is going to half. So if the concentration is halving, it means we have to use twice of these to provide the same amount as the same concentration as the other, basically. So this brings us to the end of this. Let us continue on. Question 6 says copper 2 ions form a complex with 1,2-diaminoethane. Here they've given us the symbol that diaminoethane is represented. 1,2-diaminoethane is represented by En. So they ask, with the formula given that, what type of ligand is 1,2-diaminoethane and what is the coordination number of the copper 2 in the complex? This complex is going to look like this. So there is this ligand here forming 2 dative covalent bonds. There is another ligand here with 2 dative covalent bonds, and the third ligand with 2 dative covalent bonds. So here we can tell that coordination number is basically 6 because we have 1, 2, 3, 4, 5, 6 dative covalent bonds. And then we can see, so 6, and then we can see it is basically a bidetent ligand. So the answer should be B because B has a bidetent ligand and coordination number 6. So B should be the answer. Question 7 says aqueous sodium hydroxide was added to aqueous iron 2 sulfate and the mixture allowed to stand. What would be observed? Let me write something down here. If you have aqueous iron 2 sulfate, it's basically going to be something like this. Because if it's aqueous, it means the iron 2 is going to dissociate or break away from the sulfate, creating this kind of complex, this 2 plus, and the sulfate is going to be basically there like 2 minus. So basically it's an ionic bond, but it's dissociated. So we have the water ligand surrounding the iron. So this is going to be what you observe. However, when you react with sodium hydroxide, so plus sodium hydroxide, of course, 2 of those are going to react. Let me remove the sodium and just go with OH. When you use sodium hydroxide, we will create something like this. So HOH2. And then H2O. These are going to be 4. and this is going to be a precipitate, which is going to be green in color. So it's going to be a green precipitate. And then when we allow it to stand, and again this question is asking immediately after sodium hydroxide is added, a green precipitate is going to be observed because this is a deprotonation reaction. Deprotonation reaction because these are the ligands. Let me use a different color. That two of the water ligands are going to lose protons to this. So we will produce that plus 2 water molecules on the other side in that deprotonation reaction. And then when we allow it to stand, there is going to be some oxidation occurring. Oxidation will occur where the iron 2 in this complex is going to be converted to iron 3, and then will form another complex similar to this. This is still going to be a precipitate. So that precipitate is going to turn brown due to the oxidation of the iron 2 to iron 3 by the oxygen in the air. So the answer ends up being D. I will continue to the next part. Question 8 says, when aqueous ammonia is added to an aqueous solution of zinc sulfate, remember again they've said aqueous solution of zinc sulfate, so it should be zinc 2 plus and SO4 2 minus. They say a white precipitate forms which dissolves in excess, again this is very important, in excess ammonia to give a colorless solution. We know that zinc is going to dissolve in excess ammonia because a ligand substitution reaction will occur. In the end, we're going to have ammonia ligands attached to the zinc 2 plus. So when they ask what type of reactions are occurring, the precipitate is going to be a deprotonation reaction. So when that deprotonation reaction occurs, initially it's going to be deprotonation, and then when we add, of course, more or excess ammonia, then a ligand substitution reaction will occur. So here the answer should be A. A deprotonation reaction occurs. The deprotonation is going to be basically that. Let's see. So if you have this 2 plus, when you add ammonia, they are going to be basically 2. In this deprotonation reaction, we're going to form something like this. These are going to be 4 and then OH. Here they're going to be 2. That is the solid or the precipitate plus 2 NH4 plus. So it means each of two of these water ligands are going to lose their hydrogen ions to the ammonias, creating ammonium, and this is what you're going to observe as the precipitate, white precipitate. When you add ammonia here, then we can get a colorless solution due to the ligand substitution reaction. So I will go on to question 9. Question 9 says benzene is sometimes represented by a Kekulé structure. So they're going to say, if these were the only structure of benzene, what would be the total number of isomers of dichlorobenzene? Now here I draw for you the structures or the possible isomers. I drew the Kekulé structure, and you can see if the chlorine is on carbon 1 and carbon 2, that is going to be different if it's on carbon 1 and carbon 3, which is different from carbon 1 and carbon 4. These three structures are easy for students to identify that they are different. However, some students can confuse this structure here to be the same as this. However, 1, 2, if it's Kekulé, and the other, this 1, 2, they are both 1, 2, this is 1, 2, and that is 1, 2. However, if you observe the 1, 2, here the chlorines are between a double bond, yet here they are between a single bond. Remember, in Kekulé structure, we do not assume that the double bond is moving positions. We actually assume they are restricted in position. However, in the real benzene, they are not restricted. They are the electrons in the double bond are delocalized all over, or you would say the pi electrons are delocalized all over. But in Kekulé, we would not assume that. So here we can see this is going to be the fourth structure, which would be exactly 1, 2 as this one, but they're going to be different because they are isomers. So here the answer should be a C. I will go to question 10. Question 10 says, what is the product when benzene reacts with fuming sulfuric acid? When benzene reacts with fuming sulfuric acid, this reaction is a sulfonation reaction, and the product is going to be benzene sulfonic acid. So in this case, you need to know that this is what is going to be attached to benzene, and this is attached in this form. So basically, it's going to come, the OH is on the other side, the 2 sulfur oxygen double bonds are going to be on one side, and then this here is what is going to attach onto the benzene structure. So that is why this is wrong, that is wrong because there is no hydrogen, this is wrong because it attaches with oxygen, this one here is wrong because we have 2 hydrogens. This is the correct structure, so here the answer is going to be a D for question 10. Let's move on to question 11. Question 11. Hydrogen bonds are formed when methylamine dissolves in water. Which structure best represents a hydrogen bond between methylamine and water? What we need to know is a hydrogen bond between amines and water should be formed between the nitrogen on the amine. Let's assume this is an amine. The lone pair on the nitrogen on the amine, and on the other side, the hydrogen in the water molecule, basically. Remember the water molecule here, partial negative, partial positive, so we call that a dipole, or dipoles are formed. So this should be the hydrogen bond, and that bond angle should be 180. So this is a hydrogen bond between the lone pair on the nitrogen of the amine and the partially positive hydrogen from the water molecule. So this would work, however, that this bond angle is not 180, so we cross out A. When we go to C, you can see this is not the nitrogen. Again, remember, it should that these these hydrogens on the alkyl side cannot participate in the hydrogen bonding, so we cancel that out. It's in the wrong position. The same thing here, these cannot participate in the hydrogen bond. So the only correct answer is part B, because you can see there is a lone pair, you can see here on the nitrogen of the amine, and on the other side we see there is a water molecule connected. So the lone pair here and the hydrogen bond connecting to the hydrogen, and that bond angle is 180, so that should be the correct answer, B. The next part says which type of compound cannot be a monomer in the formation of a polyamides, basically. Now you guys know that formation of amides are examples of we could form them when they're partly, we can make them in the process of making proteins. So in this case, amino acids can actually combine to form two different amino acids can combine to form proteins actually, which are polypeptides. So those are polyamides. And then we can see when they say diacyl chlorides can combine with diamines to form polyamides, basically. And then diamines can combine with diacyl chlorides to form polyamides as well. So B, C, and D makes sense. However, A does not make sense because you cannot combine two amides and end up forming a polyamide or polyamides, which is wrong. So the answer, that is wrong. Remember, we are looking for something that cannot be a monomer. A cannot be a monomer. Remember again, amino acids can be linked to form proteins, and proteins are polypeptides, basically. Diacyl chlorides and diamines and diacyl chlorides all can be used to form polyamides. So I will continue to the next part. Question 13 says, alanine is an amino acid. Which structure best represents alanine at high pH? High pH could be maybe pH greater than 7, higher enough, basically. So here we can see the first structure, part A here. This is only observed, or this structure can be observed when the pH is near neutral. So we can also see this one here is going to be observed at a very low pH, because you can see it means there was some hydrogen ion that was not part of the amine, that was the amino acid that came in and linked to the NH2. Remember, this structure would have been like this initially. See, NH2, and then a hydrogen here, and something like that, or H. So it means the process that leads these to become NH3, there should have been some protons that were in solution, meaning that solution was acidic, so that this lone pair actually was donated to that to produce NH3, the structure you see here. So that should have been in low pH, meaning there were free protons that were able to come in and basically receive the lone pair from the nitrogen. And you already know this is going to occur near neutral pH because, and again, remember this was a carboxylic group. The hydrogen in the carboxylic group was lost in solution and it combined to this part, forming a zeta ion. So that is also going to be observed near neutral pH. The only correct answer for high pH is going to be B. And that's what is the answer for question 13. It's going to be at high pH, because at high pH, a hydrogen ion is lost from here, but actually it is not taken up by this. It means it went somewhere else, meaning there are so many OH ions that are going to react with that lost hydrogen from the carboxylic group, producing water, not allowing the hydrogen to actually be able to be taken up by this nitrogen on the amine. And again, remember, the amine part makes that the amino part of the amino acid to be a good base. But if that base wasn't strong enough to accept the protons, it means there was a stronger base or alkali, like OH minus ions, that was strong enough to take up the hydrogen ion as soon as it was released. So this is the only logical answer. The answer should be B. I will go to the next question. It says, alanine is a crystalline solid at room temperature. What are the main forces broken when alanine melts? Again, remember, when they say at room temperature it's going to be a solid, it means it's a zero ion. And remember, actually, it could be ionic. That is ionic. So they ask, what are the main forces broken when alanine melts? When alanine melts, we break ionic bonds because in solid state, it's going to be an ionic compound. So the answer should be D. There are no covalent bonds, there are no hydrogen bonds, and no London forces that are broken when we melt this structure. I'll go to question 14. Question 14 says, an aliphatic organic compound has the infrared spectrum shown below. So we can see the infrared spectrum, and then they've given us what are the bond stretches responsible for the peaks P and Q in the spectrum. So if you use your data booklet, you will observe that the peak P is actually going to be due to the carbon hydrogen. It is not going to be due to the OH because it's too sharp in comparison to where the OH would be found. So it's going to be the carbon hydrogen for the aldehyde, while this one here is going to be carbon oxygen for aldehyde. This is carbon hydrogen for the aldehyde. The reason it's too sharp to just be an oxygen hydrogen. And then this one here, you can see the range in which it is shows you that it's going to be carbon oxygen for aldehyde. So based on the answers you observe here, it's only going to be part D that gives you the right answer. Carbon hydrogen aldehyde, carbon oxygen double bond aldehyde. So the answer to question 14 is a D. Let's move on to question 15. Question 15. How many peaks are there in a carbon-13 NMR spectrum of methyl cyclohexane? So here we can begin by looking at the structure. I always like to draw the carbons in so that I can avoid any confusion. So drawing in the carbons, you can see that this carbon is in an environment that is different from these two. However, these two are the same because on both sides they're surrounded by the same thing. And you can see this one here and that are the same, while this is different from that. So we can see we have environment 1, environment 2, environment 3, environment 4, and environment 5. 3 and that 3 are identical, and these 2 and that 2 are identical. So we end up with 5 different environments, or 5 different carbon-13 environments. The answer for 15 should be a C. Then the next part says, in a high-resolution proton NMR spectrum of propan-2O, they've given you the structure. They say there are. We need to draw the structure. They're asking you whether they are singlets, they are doublets, or heptads, and so on. So when I draw this structure, I realize that this environment is actually identical to that environment. So in this one environment, we have 6 hydrogens, meaning if you use the N+1 rule, basically, I'm going to talk about that, the splitting button, but let's just see. In this environment, we have 6 protons. In this environment, we have 1 proton. And in that environment, we have 1 proton. So using the N+1 rule, we can see that this proton here is going to be a heptad because the neighbor carbon has 6 protons. Using the N+1 rule creates a heptad. So environment B is a heptad, while environment A is surrounded by just 1 hydrogen. So 1 + 1 creates a 2 using the N+1 rule. That is going to be a doublet. So we can see this is a doublet. That is a heptad. And this is not surrounded by any hydrogen, meaning it's going to be a singlet. Using the N+1 rule, 0 neighboring hydrogen plus 1 creates a 1, so it's going to be split into a singlet. The answer should be A, 1 singlet, 1 doublet, and a heptad. So for question 16, that is the answer, A. The last question for section A is question 17. It says, what is the maximum volume of oxygen gas measured at room temperature and pressure required for the complete combustion of 9.2 grams of this compound? So here we can see what we need to know is they've given us the mass and we know what the compound is, so we can be able, they've given us actually the molar mass here. So what we need to do is write the formula so that you can be able to find out the mole ratio. If this compound burns completely, remember they said complete combustion. If it burns completely in oxygen, the only two products should be carbon dioxide and water. So begin by writing a balanced equation. This shows you that it should be 7/2 moles of oxygen. Now, since I know this mass, I'm going to use the molar mass given here to find the number of moles of this organic compound. So number of moles of the organic compound is 9.2, which is the mass, divided by the molar mass 92, and it gives me 0.1 mole. So I want to find the volume of oxygen. Since I know the number of moles of this, I multiply by 7/2 to find the number of moles of the oxygen gas. And then I can use the molar gas volume equation to find the volume of gas. Since they told us here that the molar volume of gas at room temperature and pressure is that, it means the reaction was carried out at room temperature and pressure. So volume of gas should equal to number of moles times the molar gas volume, which is 24 decimeter cube per mole. So 0.35 times 24 gives me 8.4 decimeters cube. So my answer should be a B, as you can see here. This brings us to the end of section A of this paper. Please do not forget to subscribe, and I hope you can be there in our next video. I'll be discussing section B, and below in the description box of this video, I will put the link to section B. Thank you so much. See you next time. Bye-bye.